Question 1 is a rates question. You can see that we've been given an equation, some information about the reaction that we don't really need to answer the question, and a table of some results. Underneath the table we have the first part of this question. It's telling us that the results were obtained by plotting a graph of concentration against time. So we're dealing with a concentration time graph. Bromine is a reactant, so we're going to have a downwards curve like this. And it says, how could we obtain the rate from this graph? Well, if you remember concentration time graphs, we draw tangents and we calculate the gradient. So tangent and gradient. I'm asked to draw a graph involving rates that shows me the order of reaction with respect to bromine. I should know from that then that I'm drawing a rate concentration graph. If I'm going to do the graph correctly and get the marks, then I'm going to need to make sure my axes are correctly labelled, including units. So my first mark will be for getting the axes the correct way around and labelling them. Second mark for a graph will be for adding a suitable scale. So for that I'll need to look back at the data in the first part of the question, and then I'm going to add a scale to this graph. Second mark in this section of the question will be for having a suitable scale on both axes. So you can see that it's a linear scale, as in it's going up in equal values each time on both axes, and I've used as much of the graph area as I possibly can. Final thing I'm going to do is I'm going to actually plot the data, and then I'm going to add a line of best fit. I've now plotted the data points. Usually a mark scheme will allow you to be within one small square of where it should actually be. Finally I'm going to add my line of best fit. You can see I've now added a line of best fit, and I'm ready to move on with the rest of the question. Underneath it says, from the graph, I'm going to find out the order of reaction, the rate equation, and the value and the units of the rate constant. Let's take a look at the graph. We can see that our rate concentration graph is a straight line, which means that rate is directly proportional to concentration. So the order with respect to bromine is first. Next I'm going to introduce the rate equation. So if I look back at the data on the previous page, I can see that in the equation there are two reactants, 1, 2. The question tells me that the concentration of methanoic acid is constant throughout the reaction, so I can ignore the methanoic acid. The only thing I need to include in the rate equation therefore is bromine, so I'm going to say rate equals K Br2. I don't need a power because it's first order. Next I'm going to rearrange to get K, and then I'm going to substitute in some data. Look at the data. I'm going to pick the first row. It's got a complete set of data in it. I could use any row out of the table, it would always give me the same result, but I'm just going to use the first one because it's usually the one that's on the mark scheme. And I'm going to substitute those numbers into the rate equation that I've just done. Finally, I need to do the units. So on the top here, I've got rate in moles per decimeter per second. On the bottom, I've got concentration in moles per decimeter. Cancel those down, and I'm left with per second. Definite awarding of marks. So 1 for correctly getting the order, 1 for the rate equation, 1 for the rearranged rate equation, 1 for the numerical value of k, and 1 for the units. Question 2. Question 2 asks me to draw a diagram showing the Boltzmann distribution of molecular energies. This is a synoptic question from AS. Must remember that a Boltzmann curve starts at 0, 0, sharp increase, tailing off but never meeting 0. Key points about this curve: sharp increase here, doesn't ever meet the horizontal axis and doesn't curve back up at the end. 1 mark for the diagram. Underneath it says, explain qualitatively using the Boltzmann distribution diagram the effect of temperature on the rate of reaction. For that, I don't really need to write anything. I'm going to draw a second curve. So, second curve, we've got 1 mark for having a correct distribution at higher temperature, so it's flatter, it's slightly shifted to the right, and we've got more molecules above here. On this graph we're also going to add activation energy, and the fact that it stays the same for both curves will gain us the second mark. And then we're going to finally label this bit and say so once more through the marks. First mark is this one for my original curve. In part B, 1 for my higher temperature curve, 1 for the fact that EA stays the same throughout, and 1 for this labelling of these extra molecules that can react. That's the 3 there. And we've got this, explain the effect of temperature on the rate constant. So if you think about what happens at higher temperatures, let's look at a rate equation. Right, if we think about what happens at high temperatures, well, at high temperatures, rate increases. We're not changing the concentration, we're changing the temperature, so this stays the same. If this number gets bigger, and this one stays the same, then the only thing that can change the rate is K. So at high temperatures, K must increase. So 1 mark for saying the rate constant increases, and then 1 mark for explaining it. Okay, so we said if the rate increases but the concentration is the same, then the increase in rate must be due to the change in the rate constant. So look at the equation again. If rate gets bigger, concentration stays the same. So the only way that this term is going to get bigger is if K itself increases. So when the temperature increases, it must be K that gets bigger. Question 2. Question 2 asks me to draw a diagram showing the Boltzmann distribution of molecular energies. This is a synoptic question from AS. Must remember that a Boltzmann curve starts at 0, 0, sharp increase, tailing off but never meeting zero. Key points about this curve: sharp increase here, doesn't ever meet the horizontal axis and doesn't curve back up at the end. 1 mark for the diagram. Underneath it says, explain qualitatively using the Boltzmann distribution diagram the effect of temperature on the rate of reaction. For that, I don't really need to write anything, I'm going to draw a second curve. So, second curve, we've got 1 mark for having a correct distribution at higher temperature, so it's flatter, it's slightly shifted to the right, and we've got more molecules above here. On this graph we're also going to add activation energy, and the fact that it stays the same for both curves will gain us the second mark. And then we're going to finally label this bit and say so once more through the marks. First mark is this one for my original curve. In part B, 1 for my higher temperature curve, 1 for the fact that EA stays the same throughout, and 1 for this labelling of these extra molecules that can react. That's the 3 there. And we've got this, explain the effect of temperature on the rate constant. So if you think about what happens at higher temperatures, let's look at a rate equation. Right, if we think about what happens at high temperatures, well, at high temperatures, rate increases. We're not changing the concentration, we're changing the temperature, so this stays the same. If this number gets bigger, and this one stays the same, then the only thing that can change the rate is K. So at high temperatures, K must increase. So 1 mark for saying the rate constant increases, and then 1 mark for explaining it. Okay, so we said if the rate increases but the concentration is the same, then the increase in rate must be due to the change in the rate constant. So look at the equation again. If rate gets bigger, concentration stays the same. So the only way that this term is going to get bigger is if K itself increases. So when the temperature increases, it must be K that gets bigger. This question is about phenol. Phenol is a compound that you will learn more about in F325, but you know enough to answer this acids question in F325. First bit, what is meant by a Bronsted-Lowry acid? You'll know in F325 we use 2 definitions for acids. The Bronsted-Lowry one is proton donor. Weak acid, you should know, means that it is partially dissociated. Underneath that, slightly more difficult question, so we're looking at conjugate acid and bases. So we look at this bit, we've got phenol over here, we've got phenol minus a proton, which means that it's being a proton donor, so this means that it is behaving as an acid, and its base pair is this one. OH minus goes to H2O, which means it gains a proton over here, so here it's behaving as a base, and this is its conjugate acid. 1 mark for correctly labelling each pair, so A1 and B1, 1 mark, B2 and A2, 1 mark. Underneath that, we're talking about a solution of phenol in water. First thing to notice, concentration is given in grams per decimetre. We don't work in grams per decimetre, we work in moles per decimetre. So the first thing we're going to do is to convert that number into moles per decimetre. For that we're going to use N equals M over MR. Okay, so I've worked out the number of moles. If it's 38 grams per decimetre, then it's now 0.404 moles per decimetre. That will be my first mark. Next I need to find the concentration of hydrogen ions. So if I am using my equations, I can see that phenol is a weak acid. We're not talking about buffers, so I know that I'm going to be using the square root equation. Okay, so to work out the H+, I've used the square root equation for weak acids. I've substituted my numbers in. I've found the square root. I should always make a point of showing all of my work in, because I get 1 for the final answer, and in this section here I will be awarded a method mark. Final bit, if I've got my H+, I'm going to use pH equals minus log H+. Final answer, final mark. In part D of this question, we're given an unknown compound that you're not familiar with, and you're asked to explain how you could make a buffer with this compound. So, this compound contains 2 phenol groups shown here and here. When you've covered F324, you'll know a little bit more about phenol, and you'll know that these 2 groups have acidic hydrogens. So we're going to start off by looking at how we'd make a buffer out of this. You should know that a buffer is made by partially neutralising an acid. We've just said that the 2 hydrogens here and here are acidic, so the thing that we would add to this to partially neutralise it would be a base. So we could add sodium hydroxide, and we'd get 1 mark for saying that. Now, if you are looking at the mark scheme, you'll see that the mark scheme says there is 1 mark for writing an equation that looks like this. Now, this question is not a recent F325 question. If this was an F325 question, I would expect that you would have to write an equation showing the structure of the whole thing. So remember, the buffer equation is exactly the same as what you draw for a weak acid. So if this is going to behave as an acid, we're going to draw it over on this side of the equation, having lost a proton. I'm going to go for this one. Both of these phenol groups, it wouldn't matter which one you took. That would be the buffer equation. So if we add acid, we would get this. Reacting with the H plus from the acid. So 1 mark for your equation for it reacting with an acid. 1 mark for saying what happens to the equilibrium. Well, if we're forming this, then that means equilibrium shift left. Okay, we're forming this compound, so this equilibrium is shifting to the left. And we're going to talk about adding alkali. One for saying that the OH minus added will react with H plus to make H2O. Remember, that is always the same for any buffer. If you add alkali, it's always the same equation. And then 1 mark for saying equilibrium shifts right. Look back at your buffer equation. If the OH minus is removing H plus ions, then this whole equation is going to shift to the right to replace the H plus. If you're looking at this in conjunction with the mark scheme, you will see that I've gone into more detail than the mark scheme. That's because I think that on a more recent F325 exam, this is more in line with what you'd be asked to write. Question 4. This question is an acids question. Specifically, this is asking about bases because we've got Kw here. So, I'm going to read the question. We're provided with 0.1 molar sodium hydroxide, 0.1 molar ethanoic acid. It says calculate the pH of 0.1 molar sodium hydroxide. So we know that because this is a strong base, the concentration of OH minus is 0.1 moles per decimeter. We know the Kw expression is this, and we can rearrange that to give us H plus. Substitute in the numbers. Okay, that number will be our first mark, so we've calculated the concentration of H plus, that's in moles per decimeter, and then we're going to calculate the pH, so we're going to use minus log, and the pH is 13, and that'll be the second mark. Moving down, we're looking at the second question, so it says we're adding 50 centimeters cubed of 0.1 molar sodium hydroxide to 25 centimeters cubed 0.1 molar ethanoic acid. So the endpoint for this reaction is going to be at 25 because the ethanoic acid is going to be the limiting reagent. So we're going to sketch a titration curve of this. So the first thing I'm going to need to do is add a suitable scale. So if I'm adding a total of 50 centimeters cubed of sodium hydroxide, and up the side I'm going to put pH, so that's going to be Okay, so if I think about where I'm starting. Okay, so I'm now going to plot the titration curve. If I look up at the top of the question, here I can see that the ethanoic acid's got a pH of 2.9, so I need to make sure that I am starting at 2.9 on this graph. I've just said that the end point, or the equivalence point, is going to be at 25 because the ethanoic acid is going to be the limiting reagent and there's 25 of it. And if we're using sodium hydroxide, we look up at question 1, we decided that the pH of the sodium hydroxide would be 13, so this curve needs to end at 13. So then I'm going to draw a titration curve. Obviously you will be doing this with a ruler. And making sure that it was correct, as I'm doing now. Okay, so marking points for this graph. We've got correct axes, so pH and volume sodium hydroxide with an appropriate scale on both. That's 1 mark. We've got, it starts at pH 2.9 and ends at pH 13. We've got the vertical section is at 25 centimetres cubed, and it says the vertical section is between pH 6 and 11. So actually I'm going to need to make a change to mine very slightly. Okay, so we've got vertical section, pH 6 to 11, 1 mark, and the correct general shape, so it's an S-curve, 1 mark. Part C is asking about indicators. It says that phenolphthalein is a suitable indicator. If you remember, a suitable indicator must change colour in the vertical section of the graph, so if it's suitable, that must mean this. That will be the first mark. And the second mark, it says methyl orange is not suitable. Okay, so we've said why phenolphthalein is suitable, because it changes colour in the vertical section of the graph. And we've said why methyl orange is not suitable, because it doesn't change colour in the vertical section of the graph. Next bit of this question. So a student repeats it with 25 centimetres cubed of 0.05 molar ethanoic acid instead of 0.1 molar. So we're halving the concentration of ethanoic acid. So a couple of differences. One for saying that the endpoint of the vertical section okay, if you think back to the graph on the previous page, we put the vertical section at 25 because that was the amount of ethanoic acid. If we're halving the concentration of it, then it's going to end half as soon. And the second mark for saying that it's going to start at a slightly higher pH. Okay, the ethanoic acid that we're using is weaker, therefore it's not going to be as acidic, so it's going to have a higher pH. Total for this question is 11. That's the end of question 4. Question 5. Question 5 is about transition metals. So we're looking at the platinum complex PtCl4NH32. So if we're going to work out the oxidation state of the platinum, we need to think that we've got 4 times Cl minus, so that's a charge of minus 4. NH3 is neutral. Overall no charge, so therefore the platinum must be plus 4 to balance out the minus 4 of the 4 chloride ligands. Now it says this complex has 2 stereoisomers, so we're going to draw the shape of these 2 isomers. So we've got platinum with 6 ligands around it, so therefore it's going to be octahedral. That would be 1. You can see that the 2 similar groups here are 90 degrees apart, so this would be cis. And in this example, the 2 similar groups are 180 degrees apart, so this one would be trans. It says include bond angles, so the bond angle in an octahedral complex is 90, so I'm going to leave that there. So I'll get marks, 1 for the bond angle, 1 for this complex, and 1 for the trans complex. Part B is about cis and trans platin. This is a complex that you should have learned in your studies of transition metals, and you should know that it is square planar, so you should be drawing square planar complex. So we've drawn the shape of the 2 isomers. It's not asking us to label them, but I'm going to do that anyway. So this is trans because the 2 similar ligands are 180 degrees apart, 2 similar ligands are 90 here, so this is cis. 1 mark for each complex. Underneath that it says explain how cisplatin acts as an anti-cancer drug, so we get 1 for saying that cisplatin binds to the DNA of cancer cells, and 1 for saying stops the cancerous cells from reproducing. Underneath that we've got another question about complexes. So it says cisplatin has several undesirable side effects. So we found some other complexes that are less toxic, and one of them is this. You should recognise that this bit here is the ligand ethylene diamine. So we've got the bidentate ligand here. That's going to be 2, and there's 2 chlorines, so it's still going to be square planar. So there is my EN ligand, and then I'm going to put 2 chlorines on here. So 1 mark for drawing that correctly. Next we've got 1,2-diaminobenzene, so let's draw that side over here. There's benzene, position 1, position 2, amine groups. We should note nitrogens have lone pairs, so that's where we're going to get the coordinate bonds forming. It's got the empirical formula PtCl2 C6HAN2. Okay, so if we look at this, we've got 6 carbons, 1, 2, 3, 4, 5, 6, C6, H's, 1, 2, 3, 4, 5, 6, 7, 8, N, 1, 2. So this bit here is one of this compound. So we'll draw that now. It's going to be square planar again because it's a platinum one. So that's going to be the first one. And then if we look at the second complex, we can see that that is equal to 2 of these. But it's talking about 1,4-diaminobenzene, so that's going to be benzene again, position 1, 2, 3, 4, 2 NH2s. Okay, so in the second complex we're going to have 2 of these. So there is square planar again. Join one on. I said it's cis, so they've got to be 90 degrees from each other, so the other one's going here for me. So that's my second complex. And then I've got to explain it. So I'm going to get 1 mark so far for each of the complexes. And then I'm going to explain this. So if I say 1,2-diaminobenzene, which is the top one up here, is a bidentate ligand. So 1 mark for saying that. And then I'm going to explain why 1,4 can't do that. So 1,4 Okay, so what we're saying there is that the 1,4-diaminobenzene, so this one here, although it's got 2 lone pairs on the nitrogens, it can't physically bend itself around to get onto these 2 bonds around the platinum. It's not possible to bend that molecule to make 2 coordinate bonds, so therefore it can only act as a monodentate ligand. So that'll be my 4th mark for this question. Total for the transition elements question in this paper is 13. Question 6. This is also a transition metal question, but it's also mixed in with some electrode potentials. We'll start off with part A. It says molybdenum has the electron configuration shown here, and it says complete the electron configuration for molybdenum 3+. So that means it's lost 3 electrons. So what we're going to do is we're going to take away the 1 from the 5s, and we're going to take away further 2 from the 4d, leaving us with 4d3. It also says
use this to explain why molybdenum is a transition metal. So we think back to our definition of transition metals. We say that so we've got our definition of what is a transition element, and we're going to use that to explain why molybdenum is one, and that's because it forms an ion with an incomplete d subshell. Following on from that, we've got some electrode potential data. So it says molybdenum oxide can be oxidized by dichromate ions, which are shown here, and then we've got some half equations. So what we're going to do is we're going to look at the electrons. We can see there are 2 electrons here in this half equation, 6 in this one. That means that we're going to times all of the top equation by 3. And then we're going to add them together. So what we should get underneath is this. Next I'm going to cancel it down, so I can see I've got 6 electrons on both sides. They can go. Over here there's 14H plus, here there's 12, so I'm left with 2. And I've got 6 waters here, 7 there, so I'll get rid of that, and I've just got the 1. Final equation I'm going to write underneath. That I've now written final equation, having cancelled everything down. It will be 1 mark for getting the correct equation and 1 mark for correctly cancelling out the species that are on both sides. Moving on to part C. So it says the redox potential for the molybdenum and molybdenum 3+ aqueous system is minus 0.2 volts. Describe how this standard electrode potential can be determined. Now that gives it away and says that we are using the hydrogen half cell. So I'm going to draw that here. You can see I've drawn a hydrogen half cell. I haven't labelled it yet. We're going to look at the other side. So if I look at this half equation, I see that molybdenum is a solid, which means that I can use a metal electrode. So I'm going to draw my other half cell here now. See, I've drawn the metal electrode in contact with its solution of ions. Now I'm going to complete the circuit by adding a voltmeter and a salt bridge. See that I've now made a complete circuit with a voltmeter and a salt bridge. The salt bridge must be labelled. For the voltmeter, a V will suffice. Have a look around your circuit and make sure that there are no gaps, because if you leave gaps you are likely to be taken a mark off. Last thing we're going to do is to label everything else. So currently I've got 1 mark for a complete circuit with a salt bridge and voltmeter, so I'm going to put that 1 mark there, and then I'm going to label everything else. The thing I'm going to label are the 2 solutions. So I've got H plus 1 mole per decimeter and molybdenum 3 plus 1 mole per decimeter. I get 1 mark for saying that both of these solutions are 1 mole per decimeter. I've now labelled the fact that I've got hydrogen gas going into this hydrogen reference electrode at 1 atmosphere. So I get 1 mark for this hydrogen half cell using H2 and H plus. So I'm now on 3 out of 6. I get 1 mark for correctly labelling both of my electrodes. So this one is a molybdenum electrode. Remember we said at the top molybdenum is solid, so I can use it as an electrode. And platinum electrode over here. So both electrodes correctly labelled is 1 mark. In addition to that, because I've correctly recognised that I can have a molybdenum solid in contact with its ions, then I get a mark for correctly drawing this half cell, so that's my 5. Finally, I need to make sure I've looked at all this, so I've done the apparatus, I've done the concentrations. Conditions is the last thing that I need to make sure I've covered. So I've got the 1 atmosphere, I've got the 1 mole per decimeter, and I need to say this is at 298K. I might just put 1 atmosphere there as well to make sure the examiner knows that I'm talking about the right thing, and that's my final mark. part D, we're looking back at electrode potentials again. This time it's asking us to work out a standard cell potential. So if we think back to when we were doing standard cell potentials, you should remember that the equation is E cell Okay, so that's what you should be remembering. The EMF of the cell is equal to the positive terminal, take away the negative terminal. So let's look up here. This one is the positive terminal, this one is the negative terminal. So we're going to have plus 1.33 minus 0.20 gives us plus 1.53 volts. Next it says, is this a spontaneous reaction? Spontaneous when it refers to electrode potentials, is talking about whether the cell potential is positive or not. So we say yes, because the cell potential is positive. And then we've got limitations. So we think about the limitations. This experiment is only going to be suitable if carried out under standard conditions. And second mark, it's a little bit odd, but the second mark is about concentrations. Now you might be thinking that we're not saying anything different because concentration is mentioned in the standard conditions definition for electrode potentials, but it's usually counted as a separate mark. Okay, so we get 1 mark for mentioning that concentrations might not be 1 mole per decimetre. In part E, we're talking about ligand substitution reactions. So it says involving a complex containing copper in the +2 oxidation state. So the easiest one to pick is copper hexaaqua or hexaaqua copper. So if we identify the correct complex or a correct complex, we'll get 1 mark for the identification of this complex. And then we're going to do ligand substitution. So we've got a couple of choices. I'm going to add chloride ions to mine. This first example, which would give me tetrachloro cuprate 2 and some water is left over. Okay, it's not asking for state symbols, so it's not bothered whether I do them or not. So I'm going to get 1 mark for the equation, and then it says include the colour change that happens during the reaction. So this complex is blue solution, and this one is yellow. So I get 1 mark for the colour change. You could have given an alternative example, still using copper in that +2 oxidation state in the hexaaqua copper ion, but instead of chloride you could have used ammonia. And in this instance you would have had 4 water molecules left over. So again, if I was going to use this as my example, it would be 1 mark for correctly identifying this, 1 mark for the equation and 1 for colour change, which is pale blue solution to dark blue solution. In part F, we're adding sodium hydroxide to copper 2 chloride. You should recognise as soon as you see sodium hydroxide, this is a precipitation reaction. So we should have Cu2 plus, and it does say we need state symbols. So we've got copper 2 plus aqueous plus OH minus, and that makes copper hydroxide. So it will be 1 mark for the equation and 1 mark for the state symbols. Is an empirical formula question. You may well get an empirical formula as a synoptic question. The steps are exactly the same as you would have followed in F325. So the first one we're going to do is convert all those masses into moles. Okay, you're going to get one of your marks for correctly working the number of moles of everything out. Finally, we're going to do the ratio. You should remember, for doing the ratio, we identify the smallest number and we divide everything else by it. And the numbers I get for this are 3 to 1 to 4 to 4. If you've got an old mark scheme, you might find that this is different to the mark scheme, but if you follow the calculation through, this is the correct answer. So the final answer is K4 Cu, apologies, K3 Cu C4 N4, and you'll get 1 mark for that. Remember, you always have to write out your formula for an empirical for that final mark. So deduce the formula of the copper 2 complex ion. All you need to do here is write down what you found up there. So the metal comes first, and then you can put everything else after it. So C4 N4. Remember, potassium is a positive ion. Complexes don't contain positive ions as ligands. This is just going to be there to balance out the charge on the complex. So if there are 3 potassiums, that must mean that this is 3 minus. Is a back titration question, a redox titration question. Remember, redox titrations are very synoptic with moles. So let's have a look at this question together. So it says brass is a copper containing alloy which is used for decorative purposes. That's of absolutely no use for answering this question. Down here we're talking about a sample of brass. So form a mental picture. There's a sample of brass, and I want to know what percentage of that brass is copper. The mass of this sample is 0.5 grams. It says it there. I'm going to dissolve this up or react it in some way to convert the copper that's in there into copper 2 plus. That's here, and I'm going to react it with iodide ions to make iodine. I'm then going to react this iodine with thiosulfate because this reaction gives me a colour change that I can see. So, reading the question, and we keep talking about kind of mark grabbing techniques, and if you look at a question and you don't know what to do, find something in it that you can do. So let's look down here and you can see there's a volume and a concentration. So straight away you should be thinking, use your moles calculations from last year. All you need to do is put these numbers in. Okay, I've worked out there moles of thiosulfate, and that's the first mark. So even if I'm completely stuck on this question, I can use an AS moles calculation to give me one of the 4 marks. That's a quarter of the marks on this question. So now I'm going to start labelling up my equation so I know what I'm looking at. So I've just worked out moles of thiosulfate, that's here. So then I can use my molar ratio to get moles of iodine. I can see that it's 2 to 1. So I'm going to divide that by 2. If I know the moles of iodine here, then I know the moles of iodine here, because it's the same portion of iodine that we're talking about. And finally, I can work back using my molar ratio to the copper 2 plus, which again I'm multiplying back up 1 to 2. So my moles of copper 2 plus is that. So down here I'm going to write and even though it's the same number, because I've said that's moles of copper 2 plus, that's my second mark. Now we're just going to use standard moles calculations. So I want to know the mass of copper, so I'm going to use N times MR. Where's my N? So on the MR of copper. So now I know the mass of copper, that's my third mark. And then finally, if I know the mass of copper and I know the mass of the sample of brass, I can find the percentage. So it's saying this whole thing weighs 0.5 grams. There's only 0.283 grams of copper in there, so what's the percentage of the copper? That's my final answer, and I get 1 mark for that. Total for this question on transition elements and electrode potentials is 25 marks. That's a quarter of the paper. Question 7 is a lattice enthalpy question. You can see it's straight away mentioning enthalpy of solution, so you know that that's the type of Born-Haber cycle that you're going to be drawing. Remember we said that these questions are not necessarily F325 questions because we've made this paper up for you. I would think that in an F325 exam they would actually tell you whether the enthalpy of solution is exo or endothermic, so I'm going to tell you now that this is exo, which is going to help us draw the cycle, because different exam boards draw them very slightly differently. So if we're going to draw one the way that we would be expected to, we're going to start off with gaseous ions at the top, we're going to have an arrow down to our ionic solid. I've just told you that the enthalpy change of solution is exothermic. If you didn't have that information, you drew it as endothermic, you'd get the marks anyway. But if you're given the information, you must make sure that you check it. So we're going down to the ions in solution. And of course then in the middle here, we need to show one of the ions being hydrated. Okay, so there's our cycle. We've hydrated one ion and then we've hydrated the other ion. It says include the names of the enthalpy changes, so now we're going to need to do some labelling. So we should have lattice enthalpy of magnesium chloride. This one, hydration of chloride. I might just put on there that I'm going to times that by 2 so the examiner can see that I know what I'm talking about. And then up here we've got enthalpy of hydration, magnesium 2+, and down here enthalpy of solution of magnesium chloride. So we've got 1 mark for correct formulae on every line, 1 mark for all the state symbols being correct. If you're drawing a Born-Haber cycle, always go around and check that there's a state symbol and everything, because whenever I'm marking these, it's quite frequent that people just miss one state symbol and then they miss the mark. And then it says, what 1 mark for 3 or 2 correct enthalpy changes labelled, and 2 marks if you get all the enthalpy changes correct. So that's the 4. Carrying on down, we've got describe and explain the difference in the enthalpy change of hydration of magnesium and calcium ions. So we've got Mg2+ and Ca2+. You will know that these are in the same group, so we're going down a group. So if we're comparing the size of hydration of magnesium and calcium, we don't need to mention the charge, they're in the same group, they've both got a 2+ charge, so we're going down a group, we're going to be talking about ionic radius. So this is going to be our first mark to say that calcium is a bigger ion than magnesium. Remember, if you say atomic radius here, then you will not get this mark. Second thing that we're going to say is okay, so because it's smaller, because magnesium 2+ is smaller, that means it's got a greater charge density and it is more attractive towards water molecules. That's going to be my second mark. And the final mark will be for saying okay, so if it's got a stronger attraction for water molecules, it's going to have a more exothermic enthalpy of hydration, and they are my 3 marking points. Finally, in this question, I've got 3 different ionic lattices to put in order of increasing exothermic lattice enthalpy. So I'm going to start off by writing down the things I'm comparing. So I've got Ca2+ and Mg2+, the cations, and then I've got oxide and sulfide for the anions. So we're going to reason our answer out and then give the final answer. So we're going to say that calcium ions have a larger ionic radius than magnesium ions. Remember, we're either going to be saying ions or we're going to put Ca2+ and Mg2+, otherwise no marks for that. So that's going to be 1. Then we're going to say sulfide ions are larger than oxide ions. Okay, because if you remember again, this is going down a group here, so larger ionic radius, and this is going down a group, so larger ionic radius here. Next marking point, we're going to say greatest attraction between Mg2+ and O2-. the most exothermic is magnesium oxide, then it's going to be calcium oxide, then calcium sulfide. Okay, so if we think about it, through our reasoning we've decided that magnesium oxide is the most. The least is going to be the one with the two biggest ions, which is calcium and sulfide, so that's going to be the least exothermic. Calcium oxide goes in the middle. So 1 for each of these marking points.